Greetings.
And salutations.
Chapter 2, Section 6 coming at you. More rational function stuff.
Well, I don't know about more.
More.
We've done some. Okay, a rational function.
Maybe not a rational function, but we've looked at rational numbers.
We've looked at rational stuff. Yeah,
Yeah.
definitely. So what happens to make it a rational function is that we have, basically, we can split it up into two polynomial functions, a function on top and a function on bottom. So basically, we just have to have a fraction, and then bam, we've got a rational function.
Which we have seen with our synthetic division and stuff like that. We just haven't addressed it specifically like we're going to today.
Until now.
Right.
Okay, so here's an example. Find the domain of a rational function, f of x equals 1 over x minus 2.
Real quick, while we're talking about the domain of this, one thing to remember is that you just can't have 0 in the denominator. Wait, that is domain.
Oh, yes. That's how you figure out the
You cannot
domain.
have a 0 in the denominator of any rational function. It's just not a good deal.
So when we're doing rational functions, you want to take the bottom
Whatever it is.
and you want to set it equal to 0. And what we're saying is that it can't equal
That is
whatever
correct.
that
Yeah,
number
can't
is.
have a yeah.
So I'd add 2 to both sides here. And I'd very quickly come to the conclusion that x cannot equal 2. But any other number is fine.
Right.
What we're saying with this is if I plug in a 2, I get 0 on the bottom. 0 on the bottom is undefined. You can remember because it makes an upside down stick figure. That upside down stick figure is sad because he's undefined.
What
So,
if that was like a 3 up there? Could he still be an upside down
that would
stick
be a
figure?
much more awkward stick figure.
Okay.
But
all
I
right.
think you maybe could make it work.
All right, I'll work with you on that.
Okay, so to write this in interval notation now, we go from negative infinity to 2,
But we can't include the 2 because that's where the 0 happens.
and then 2 to infinity. And remember, if you put a bracket, don't change it to a parentheses like so.
No guessing game on this.
Okay?
We want to know.
Erase. Erase if you make a mistake. Because
Just
it's
like
very
that.
important that that's parentheses because it's not equal to it too.
That is correct.
And if you look at the graph on this, like I know exactly what this looks like. We would have basically a vertical asymptote
Yeah, at 2.
at 2.
Because our graph of 1 over x actually shifts 2 units to the right.
And there's also one at y equals 0. And so what happens is your graph will do like this thing, I think, if you're looking at it. And oh look, clearly there's nothing defined at 2.
Nothing at all.
But algebraically it's pretty easy.
Yeah, not bad.
And in case you're like, oh no, what about square roots? Square roots aren't polynomials, so we don't have to deal with that in this section. We just have to worry about where does the bottom equal 0.
And one of the problems that you're going to run into is a lot of times the pre-calculus kids want to make the top equal 0 also. But
Which tells us something, but nothing about the domain.
yeah, you can have the top equal 0. That's totally legit.
That gives you x-intercepts,
Yeah,
actually,
right.
which is something we're going to do
Right.
in a little bit.
So bottom only.
Bottom only for domain.
Okay, so keeping along the lines of where we are and are not defined in the denominator, we can actually describe how a graph can be obtained from the reciprocal function.
Yes, all of these, if we think back to in chapter 1, we talked about parent functions. And so most, if not all, I don't know, would you say all of them are related somehow? Maybe just most. A lot
I
of the
think most
functions,
is good.
a lot of the functions are going to be related to this g of x equals 1 over x, which remember that what that looks like as far as our parent graph goes is that we've got a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. Then we've got this cool looking thing right here in the first and third quadrants. And so what the rest of these will look like is they'll have some kind of a stretch, shrink, shift thing going on.
So it should have the general shape.
Yes, the general
Alright.
shape should still be consistent. So
Okay.
in this problem, they want us to describe how the graph of the given function can be obtained by transforming the graph of the reciprocal function, and also identify the horizontal and vertical asymptotes and use limits to describe the corresponding behavior. Lastly, sketch the graph of the function.
Wow, that's a bunch.
It's a lot of stuff.
So one thing to remember is that after we did all that practicing on sliding graphs all over the place, remember if you do something to the x, like actually to the x, it's going to become part of the super secret opposite society, which is a big deal because on this first one, without doing a lot of work at all, we're looking at that guy, and with the x plus 3 in the denominator, we're adding 3 to the x, which means that super secret opposite society, we're going to move 3 units to the right.
You mean left.
That's what I said.
Yes,
left.
we're shifting.
The opposite of plus 3.
Shift left 3. Because that plus 3 is inside of our function. Our function is 1 over x, and the plus 3 is inside of where that x is. So shift left
3 units.
3. What else is happening to this?
We also have a vertical stretch of 2 going on. Now, why do I know it's happening not to the, specifically to the x? Because notice that your x is in the denominator, and we're not dealing with a number in the denominator right now. We're dealing with the guy in the numerator. And so that would become outside, and we're going to do a vertical stretch by a factor of 2.
I'm thinking we're probably going to need some room here, so I'm just going to,
we'll do an A and B
clean
version.
it. Yeah.
Right.
Vertical stretch by 2. And those are the 2 things we've got going on. We could also end up seeing like reflections. We're not going to see typically horizontal stretch or shrink. They're not going to necessarily stick a 2 down here on the bottom. We're going to see them on the outside.
Usually.
Because of the nature of the way they're setting the problems up.
Right.
So that's the transformation. Identify the horizontal and vertical asymptotes. So the vertical asymptote, that's easy. That's where the bottom equals 0.
So
Always. That's how we find
x
it.
plus 3 equals 0. The other, if you want to work it out, do it. I usually will ask myself in my brain mentally, quietly to myself, what plus 3 equals 0?
And you get -3.
And you get -3, and that's your vertical asymptote.
So is there a slide somewhere in here that talks about how to find the horizontal asymptotes?
I believe we have addressed horizontal asymptotes, but in this
case... We
case...
talked about graphing them. Like if I graph this, like originally my parent function has y equals 0 as a horizontal asymptote,
Right.
and we didn't move up or down, so this still has to have y equals 0 as a horizontal asymptote.
One way that you could also remember that is if you think about really large numbers of x, like 2 jillion, trillion, billion, million, jillion.
Yes.
Then if you put that number into the denominator,
And you do 2 divided by...
all of that plus 3, then you get a number that's really, really close to, but not quite equal 0, and that will give us our horizontal asymptote as well.
Okay. And we'll talk more about horizontal asymptotes apparently later
A
on.
lot more.
Yeah.
There's some cool tricks.
Yeah, and then use limits to describe the corresponding behavior. So what we want to do when we use limits is we want to use a limit for our -3 that we've got, and we want to look at 2 different limits. We want to look at the limit as x approaches -3 from the negative direction.
That means from the negative side of the number line. Let's just keep it easy.
This is g of x, not f of x. So of our function.
And so as you zoom in from the negative side of the number line,
what is it getting closer to? So basically it looks like this, but we're going to pretend this is at -3 instead of it being the y-axis.
so notice on the graph at that point, I'm looking right at it's going down.
As we're getting closer to -3 from the negative
from
direction.
the negative direction.
So that's this
down,
direction.
down,
Where are we
down.
going? We're going towards the negative infinity. And so you'll see this notation in the book and here in our notes as we do it. So now we're going to approach -3 from the positive direction.
So that's coming from the other side now, which means that from the positive side of the number line, we're going to approach an x value of -3. And when you do that,
you're getting closer and closer to positive infinity this time. And those should be opposite because we were heading opposite ways whenever we came up to the asymptote for either direction.
Right.
The other type of limit we should look at is for our horizontal asymptote. That's our in behavior. So our in behavior is as x approaches -infinity, what value am I getting closer and closer to?
And that would be the actual asymptote number, which is 0. Remember, with a limit, you're looking at what happens when you get really close to a specific x value. What y value does your graph approach? And so in this case, it never actually touches 0, but it gets really, really close to 0. So that's what the limit is.
I feel like you just called me a 0.
I would never call you a 0, Mrs. Stevenson.
Okay, just so we're clear.
Right.
And then sketch the graph of the function. So we've kind of got a sketch that we've been working on up here, but let's go for it one more time.
Let's do
it. If
it.
I was sketching this, what I would do is I would say, okay, I know there's a vertical asymptote at -3. So I would draw a dotted line at -3. There's a horizontal asymptote at y equals 0. So here's our horizontal asymptote.
And remember, this is a sketch, not a perfection.
Right. And then if you need to here, we can plug in some numbers. Like we could plug in 0, which is over here, x equals 0, and we could say, oh, that's 2/3. So at 0, I would be at 2/3, which is about right here. And then that will help you realize, okay, my graph really is up in the top right. And then we can also plug in like a -4 if we wanted to. We'd get 2 over -1. which is -2. So that tells us it is down here. And that will help you figure out which part of your graph, because sometimes you end up with it in the top left and bottom right instead of the...
Right, sometimes it's kind of an upside down mirror
thing.
Yeah.
Yeah. And that's all for A.
Okay, so we're gonna look at B. Hey there.
Now we're trying part B. So this one's just a little bit tougher because this has an x on the top and the bottom, and that's not what our parent function looks like.
No, it doesn't look like that at all. We want the same general shape.
Right, so what we can do is we can use division and make it look like it. And so on these, the book generally makes you do like long division, but there's no reason why we couldn't do synthetic division.
The book, synthetic division, way easier.
So remember, if I'm dividing by x minus 2, that I change it to a positive 2. Okay.
Wow, this looks really hard. There's a lot of stuff going on.
So move the 3 down. Times.
And you probably shouldn't get a 0 in this case.
No, you shouldn't. Otherwise, you did something wrong.
Yeah.
So what we're saying, if we write this back as a polynomial, is that h of x equals 3, because remember, it's 1 degree less than what we started off with.
Start off with first degree.
So now it's 0 degrees. So 3 minus 1 over x minus 2.
Wow, that's really easy.
And now what we can do is we can say, well, this the plus 3 on the outside is telling us that we've got a shift up of 3.
Mm-hmm.
The -2 on the bottom is telling us that we are shifting right 2.
Righty. Super secret opposite society down there.
And then lastly, the negative right in front, that's a reflection across the x.
Yep.
Excuse me, reflection across the x-axis.
Reflect over x.
Because remember, they would have to actually have made the x negative. Like our negative would have to be down here on the bottom
and
for
it
to be a reflection across the y-axis.
Right.
So it's reflect over x-axis. That's our first thing. And so really, we could go ahead and draw this right now almost if we wanted to. I
Sure.
misspelled right. Let me fix
That's okay.
that.
Fix your misspelling.
Okay.
That's why we teach math, not English.
Yeah, exactly. So identify the horizontal and vertical asymptotes. Well, if we graph this...
It's easier to see the horizontal and vertical asymptotes.
Absolutely. We know from the previous slide what a normal reciprocal function looks like. We're shifting up 3, so we have a horizontal asymptote at 3. We're shifting right 2, so our vertical asymptote should be at 2, because normally they're both at 0.
Right.
And then we're reflecting over the x-axis. So instead of having our graph be at the top right and the bottom left, that means we'll be bottom right and top left. Got a little close to the asymptote there.
That's all right. And you can always check this by picking up values.
You can graph anything if you can just plug in values.
Right.
Anything you want.
We just can't use a value of 2. But we could use 3 and we could use 1 to get an idea, to make sure that you're in the same correct spots.
So again, our vertical asymptote comes from where we set the bottom equal to 0 and we solve. So our vertical asymptote is at x equals 2. Our horizontal asymptote is at
y equals 3.
Y equals 3 because we shifted up 3.
Yep.
What else do we need? Use limits.
We need the limits. So we need the limits going both ways. So we need the limit from the left and right of the x equals 2 part. We also need the limit as we go to positive and negative infinity. So a lot of limit notation here.
So for h of x, as we're going toward 2 from the negative direction, that means that we're following this line along. We're coming from the negative direction toward 2, and we're going to end up going toward positive infinity.
Yep. And for those of you that limit notation is kind of new, the correct way to do limit notation is how it's being written. Sometimes when you guys work limit notation out, you stretch it all out in one long linear look, and it isn't. It's actually limit over.
Almost like a fraction without a fraction bar.
Right.
Like these go together. We're talking about the limit as x approaches 2 from the positive direction of h of x is, and so if we follow this from the plus direction, it's going to end up going down toward negative infinity. And then our in behavior limits are going to be as x approaches negative infinity of h of x. Well, that's where our
should be
horizontal
our
asymptote is coming in, because as I get closer and closer to negative infinity, I'm getting closer and closer to 3.
And remember, with all these limits, it's what you're approaching, not what you're actually touching. So it's all about the y value that you're getting close to.
Okay, there we go.
There you go.
That's that example right there.
There you go. More vertical and horizontal asymptotes, but oh my, this problem.
Oh, it doesn't look that bad to me.
Well, it's got squareds instead of regular x's.
Okay, so this is going to be a little different. So this is a situation where this may or may not actually look like our parent graph of 1 over x because of the x squareds. I don't know. We'll just have to find out, right?
Yep, let's dive in.
Okay, so...
I'm sensing some long division, actually, for this one.
Really?
My teacher senses are tingling.
Okay, so you want to do some long division?
I don't know. Would that get us into that parent function shape thing?
I suppose it would.
Did you have another plan that was better?
I don't know.
Okay. Don't forget 0x's here, kids.
And I could put a 0x over here.
You could.
Should I do that? I don't really necessarily
No,
have
I wouldn't.
to, though.
No, let's not put it over there. But for
Okay.
sure, we need it under the division symbol there.
Okay, so x squared times what gives us x squared?
1.
So that's going to end up way
Bam.
over here. And so what we do is we multiply x squared plus 1 times 1. We get x squared. 1 times 1 is 1. But we're going to subtract this.
Subtract all of it.
So what that does is x squared minus x squared is 0. 2 minus 1 is 1. And so we end up with f of x being 1 plus 1 over x squared plus 1.
Yep.
So
that's actually a little easier to look at. Gives us a better idea.
Gives us a better idea, I suppose. What's happening here is that this number that we got in front, this 1, that's telling us what our horizontal asymptote is, right?
Because we're shifting up one unit.
Because we're shifting up 1 unit. And so we can say our horizontal asymptote is at y equals 1. And anytime you do this, if you do division, whatever that number out in front is
whatever
going to
the
be,
thing out in front is, actually.
Yes, actually, and we'll look at some other asymptotes that aren't lines that are horizontal. So whatever this is before the remainder is our horizontal asymptote. And then if you don't get anything out in front, then that means the horizontal asymptote's at 0. For our vertical asymptote, we need to look at, on either of these, the way we have them written, where does the bottom equal 0?
So x squared plus 1 equals 0.
Well, we could try to solve that by subtracting 1 over.
That's a great idea.
Square root.
Wait a second.
Oh no. So now that we've talked about real and imaginary numbers, we know that this would be plus or minus I, which is great. Those are some zeros that we have.
Those are the zeros.
But
yeah.
these are not x-intercepts because they're imaginary.
Right, because you can't cross the x-axis at an imaginary spot.
Right. And I didn't mean x-intercepts. I meant asymptotes.
You
It's
meant-
not.
yeah.
It would be an imaginary asymptote,
Right.
which is not an asymptote
Again, it's
at all.
imaginary.
Right. So vertical asymptote would be none. There is not a vertical asymptote.
No vertical asymptotes.
I'm kind of curious about what this would look like.
I know exactly what this would look like, I think.
Okay. You want to tell me about it? You want to
Well,
draw
it's
it?
going to be limiting towards 1 as we go to the infinities. How about that?
Okay.
And if I put 0 in for x,
I get 2.
you get a 2.
If I put in 1,
If you put a 1 in for x,
then that's 3 halves.
yeah. So
So is it this kind of situation?
yes, it's that kind of situation right there. I'll just double check these, but I'm pretty sure it's a little bump at the origin and flattening out on the limit.
And they didn't ask
No,
us to graph it, but
That's what
I
it's-
know we were all
I'm
curious.
pretty certain that what you have is correct.
Okay, well, so, and another way to check that is that you put in your calculator, or just plugging in more values will work.
Oh yeah, who's right?
Can I see the graph?
No, it looks just like what you drew.
Oh, okay, good.
See?
So our limits that we have to do to describe the behavior is we need to do in-behavior asymptotes for our horizontal asymptote. So as x goes to negative infinity
Of f of x.
f of x. As we go towards negative infinity, we're going closer and closer to the y value of 1. And as we get closer and closer to positive infinity, we are getting also closer and closer to 1. And then there's not a vertical asymptote, so we don't need a limit.
Yeah,
for
we
the
don't have to worry
vertical
about that. Yeah. How about that? That's a fun graph.
There you go.
Hey, this is a slide full of, I don't know, rules aren't quite the right thing, but rules.
Yeah,
guess.
there's some handy tips, tricks, whatever you want to call it.
Tips and tricks to get you through the whole world of
Graphing a
asymptotes.
function in general as well, I would say.
Right. So in behavior asymptotes, those are the asymptotes that occur as x goes towards positive or negative infinity, the end behavior. With an end behavior asymptote, we're not necessarily concerned with what's going on close to zero.
No, we're looking at what's happening towards the end.
The end, which is an impossible thing to find, but we can look at a limit as we go towards the end behavior.
And the end behavior asymptotes, most of the time, are also known as the horizontal asymptotes.
But not every time. Some of them are slanted or called end behavior asymptotes.
Right.
So there's some things that you're looking for. Number one, and we'll just go through these really quickly. If the degree of the denominator, that's the upstairs, is less than the degree of the numerator.
You meant that backwards. The
what
degree of the denominator, that's the bottom.
Downstairs, sorry. D for down.
D for down is less than the degree of the numerator.
Right.
There's no horizontal asymptote.
It's what's called an end behavior asymptote or a slant asymptote, depending on what text you're looking at.
And so a degree on the bottom less than the degree on the top, that would be like having x squared on the bottom and x to the fourth on the top.
There you go.
That's going to be a situation where we would end up without a horizontal asymptote. What we would do is we'd have to divide and see whatever that is minus the remainder. There's no remainder for it. And then that would tell us what our asymptote looks like.
The end behavior one.
Yes, the end behavior.
Part two, then, second bullet point, if the degree of the denominator is equal to the degree of the numerator. In other words, upstairs and downstairs have the same degree, the same exponent, largest exponent situation thing.
So like an x squared on top and an x squared on bottom?
Those would be the same degrees.
What you do is you take a ratio of their coefficients. And so, this could end up being like longer.
There could be tons of stuff.
All we care about is the leading coefficients of the things with the highest degree. So we would make a ratio of 3/1 and have an asymptote of 3.
The reason that we can do that is because if you take, say, 1,000,000 and square it, that's a pretty significant number.
Yeah.
But if you take 1,000,000 and then square it and get that huge number and then add another 1,000,000, it's
still a really huge number.
Big, but not quite the same impact.
So basically we can drop off whatever the other terms are and just focus on the ones that are to the highest power.
Right.
Because if you theoretically plug in infinity and you square it, well, you really don't care about the rest of it because you've already got a really, really big number.
Right. Doesn't make things that different.
Yeah.
Lastly, if the degree in the denominator is larger than the degree in the numerator, then your horizontal asymptote will be 0. Y equals 0.
So denominator larger than numerator. So that'd be like x over x cubed.
That's perfect. And the reason this is true is if you just think about how these numbers grow. If I take the number 2 and put it on the top and take the number 2 and put it on the bottom, well, 2 divided by 8 is a fairly small number. But then what happens when I do it for 100? Well, 100 divided by 100,000?
Something like that.
Is even smaller.
Yeah.
And then 1,000,000 divided by 1,000,000 cubed is even smaller. So
as you make your x values bigger, basically the bottom is going to grow faster than the top because the bottom is being cubed. So that's why it ends up being y equals 0.
So those are easy to see. Those are fun.
Vertical asymptotes. These we've talked about, but they occur where the denominator is 0. And so what you have to do is you always want to factor the top and the bottom. If something cancels out, then that's not an asymptote.
No,
that would be a hole. But I don't think that actually ends up happening in this section.
I don't think it does either, but it is something to be aware of.
But you need to factor anyway because factoring will help you find the vertical asymptotes on the bottom and it will help you find the x-intercepts because that's where the top equals 0.
Right, and if you can't factor, you can always do the quadratic formula on the bottom and get in your rational 0, which is totally possible.
Right. And then the y-intercept, a lot of times we just kind of forget the y-intercept, but if you plug in a 0
for x,
then that tells you the y-intercept.
And it gives us a place that we can actually plot a legit real point close to where we are usually looking, which is on the origin.
Right. And so if we basically this slide is going to be useful if we're asked to graph something or asked to tell this information because if we know the asymptotes and we know the x-intercepts and the y-intercepts and maybe we plug in a couple other points, then we can pretty easily graph these without ever having to pick up our calculator.
Right, and that's what we want to be able to do.
Yeah.
Okay, so find the asymptotes and the intercepts of this function and graph it.
Graph it, yeah. So this will play into what we've talked about on the last slide, because almost all of that is super helpful information. Actually, all of that I think is super helpful information.
Especially for this one. So one of the things that we can look at right off the bat is we can look at the degree of the top and the degree of the bottom. That's usually one of the easier things to see. And in this case, we've got a 3 on the top and a 2 on the bottom. So
top's bigger than the bottom. We're going to have to do some division to figure out what our not horizontal asymptote will be.
But our in behavior.
Yes, our in behavior asymptote. So
or slant.
It might be slanted. Actually, this one will be slanted, won't it?
I think this one will be, yes.
Since there's 1 degree different.
Yes,
them.
Yes.
So we only have an x cubed here, and so this is kind of like a placeholdery thing where, you know, when you have 1,000 and you try to divide, you still have those other zeros.
Yeah.
So make sure that you put those other zeros there. X squared times what is x cubed?
X.
So I put an x here above my other x, and then I multiply. So x squared times x is x cubed. Negative 9 times x is negative 9x, but we want to subtract all
the
of
whole shooting match.
So x cubed minus x cubed is 0. If I drop down this 0x squared, it's 0.
0.
And then 0x minus a negative 9x
plus
is
9x.
Positive 9x. And we can drop this 0 down if we want to, but pretty quickly we should realize, hey, I cannot multiply x squared by something and get 9x.
Can't do it. It's pretty much impossible.
So that's a remainder-y situation.
It's totally possible, but not for this problem.
Right.
Actually.
So what happens is that anytime we're looking at these in-behavior asymptotes, we only care about this first part and we don't care about the remainder. Okay, so you can actually stop whenever you start to see what the remainder is. Our horizontal asymptote, which is really our slant asymptote.
In this case, is going to be y equals x. If there was more stuff in the front, it would be, you know, x plus 3 or x squared plus 2x minus 1 or whatever.
Yeah,
but in this case,
this line,
it's
y equals x is what we've got going on.
Yeah, okay.
We found the slant asymptote as y equals x, and now I think that we should look at the vertical asymptote. And in general, one of the first things we should do when we look at a function is probably try to factor it, right?
Yeah, I agree.
So the top, x cubed, we can't factor.
No, he's done.
But on the bottom, x squared minus 9, I don't know why there's parentheses on the bottom there.
Obviously, I made this slide, and that's what I decided to put in there. So
x squared minus 9, anytime you have two things you can take the square root of.
And there's a subtraction sign.
And there's a subtraction sign. This is the sum and difference of
squares
or something like that.
Yep.
So x minus 3 and x plus 3
righto.
is what that splits up into.
Bingo, bango, bongo.
Nothing cancels out.
Nope.
But now we can set the bottom equal to 0 and solve to get our vertical asymptotes.
Which it looks like it's going to be 3 and negative 3 because nothing cancels out on top, as Mrs. Stevenson just indicated.
Right. I regret the decision of writing this out. Okay, so x equals negative 3 and positive 3.
Getting closer.
Okay, now intercepts. So how about the x-intercepts?
So the x-intercepts are going to be, gosh.
Where the top equals 0.
Has a 0, which would
x
be
cubed
at
equals
0.
0, that'd be at 0. With a multiplicity of 3. Not that it matters. It really doesn't matter that the multiplicity is 3, except that that means that it goes through instead of just bouncing at 0.
Should, yes.
Y-intercepts, we have to plug in 0 now. So 0 cubed over 0 squared minus 9 is 0.
Yep, anything with 0 on the top. Now this is a situation where 0 on the top, good, 0 on the bottom, bad. So
that's always a situation.
Yeah, don't try and create something that doesn't need to be created. 0 on the top is fine, it's just 0. We can totally do that.
Yes.
0 on the bottom is where the issues occur.
Check out my cool graph I've got going on
Wow, that's
here
amazing.
with like tick marks and stuff.
Yeah, that's wicked.
Okay, so we have a vertical asymptote at negative 3, a vertical asymptote at positive 3,
And a slanted asymptote at y equals x.
so that's a line that goes through 0 and has a slope of up 1 over 1.
A lot of crazy things going on here, including that crazy thing.
I don't know if they saw that crazy thing. Okay, now here's something that can be kind of tricky. So we've got these asymptotes going on, and so our graph that's where our graph is going to be, is it's going to be headed toward these asymptotes, but not touching these asymptotes. So you might say, hang on a second, we have an x-intercept at x equals 0, y-intercept at y equals 0, which means our graph is going through 0, 0, but there's an asymptote right there. Well, what happens is that slant asymptotes and horizontal asymptotes are only in behavior asymptotes. So in the middle, they're not very good at being asymptotes.
No, they're terrible actually.
Yeah, it's
Because we're going to cross
horrible.
that sucker. Yeah.
Horrible. So would you say at this point they should look at the graph or plug in values to figure out the
I
rest
say
of
let's
this?
just kind of check out a couple values because those are, not hard numbers to work with
Okay,
for this particular problem.
So how about like a positive 1?
Okay, so positive 1. So 1 cubed over 1 minus 9.
So
1/8.
negative 1/8.
Negative 1/8.
Which is important. So
So
we're going to
right,
be
right under the x-axis.
right here.
Yep.
And then if I plug in negative 1,
Yep. That's going to be negative 1 on the top, and then again on the bottom an 8. So it's positive.
positive 1/8.
Yep. So I would say, mostly because I'm so familiar, yes, keep going. Because I'm
We're
so
heading
familiar with the
towards the
graphs, this is
asymptote.
how this interior part should look.
So the interior part is basically going to ignore. Wow, I can't talk. It's going to ignore the slant asymptote here in the middle.
Right.
But then on either side, the slant asymptote and the vertical asymptote are both going to come into play.
Right.
So normally, if I'm headed down this direction, that means that up here I would be at positive
Yep.
infinity because it's
And you're going to
opposite.
squeeze right into that little hole right there.
And then same here.
Thing
This
on the
is
other
up
side.
top, so this will be down low.
Right.
And if you graph this and look at your graph, you'll see that while they did a better job on the calculator, this does look very similar to what we would get.
Pretty similar.
Yep.